In this video, we'll do Theorem 6.4.1, Definition 6.4.4, and Proposition 6.4.2. In the previous video, we saw a cofactor expansion along two different rows, well, actually a row and a column of a matrix, and they turned out to be equal, and the Laplace expansion theorem tells us that that is not a coincidence. Let A be an n by n matrix with n greater than 1, then the cofactor expansion along any row or any column of A is equal to the cofactor expansion along any other row or column. It means it doesn't matter what row or column you choose, the cofactor expansion will always give you the same number. This is super nice because that means that we can define this cofactor expansion to be the determinant. So let A be an n by n matrix with n greater than 1. So now we're talking about any size matrix. So not just n less than or equal to 3 like we had in previous videos. Now we're talking about any size n. Then the determinant of A is the value of the cofactor expansion. Cofactor expansion, my hands can't keep up with my mouth, along any row or column, it doesn't matter which because they will give us the same number, along any row or column of A. So now we have a general definition for the determinant of A for any size matrix n. But now there's questions here. There's some, so you should be up in arms saying, wait, we already have a definition. We have a definition of a 2 by 2 and a 3 by 3. How do we know that these are the same? Well, Proposition 6.4.2 tells us that the definitions of the determinants of the 2 by 2 and the 3 by 3 matrices that we saw in section 6.2 are indeed consistent with this 6.4.4 definition. Proof. So let's go ahead and see that. So if we have a 2 by 2 matrix, let's let our matrix A be this matrix A, B, C, D. Then the determinant of A, or the determinant of A that we saw before, CD, was A, D minus B, C, right? That's sort of cross your heart motion. Now if we do cofactor expansion, the cofactor expansion, we're hoping to show that we get the exact same value. So if we do that, we need a grid, right? We need the grid of pluses and minuses. Let's do along, doesn't matter which one we do, along row 1. How about that? So we start with the upper right corner as a plus, plus and minus. So our cofactor expansion is going to be, well, we take the entry, the sign, and the entry, so plus A times the determinant of the matrix that's left when you remove the, nope, that's wrong, the row and column of A. So we're left with the small matrix D, the determinant of D. And you notice that I've avoided using the vertical bars so that we're not confused with absolute value bars. Now, then we have B here is our next entry. Minus is the sign, so minus the entry times the minor, so the determinant of, and we will remove the row and column of B, and so we're left with the little matrix, the 1 by 1 C. And that cofactor expansion, if we then evaluate those minors, gives us A times the determinant of a 1 by 1, you remember from previous videos, is just that entry. So AD minus B times C, and there it is. It matches the same as the previous definition. So there's the 2 by 2. Right? So there's the same as the previous definition. This is the 2 by 2 case. The proposition said not only was the 2 by 2 previous formula consistent, but so was the 3 by 3. So let's look at the 3 by 3. So now let's let our matrix A be this matrix A, B, C, D, E, F, G, H, I. D, E, F, G, H, I. Again, hands can't keep up with the lips. So we are looking now to do cofactor expansion. Well, let's remind ourselves actually, right? Let's recall. Let's recall that the determinant of A, what we did before using Sarris's rule, so A, B, C, D, E, F, G, H, I, was we rewrote those first two columns, A, D, and G, B, E, and H, and then we did a basket weaving method, right? So we did A times E times I plus B times F times G plus CDH, and then subtracted GEC plus HFA, and then plus IDB. So that was our previous value. So now what we want to do is cofactor expansion and show that we get the same result. So cofactor expansion, and again, let's choose row 1. It can be any row or column, so I've got to choose one of them, and row 1 is as good as any. So cofactor expansion along row 1, which means I need my grid of plus and minuses. Plus in the top left corner, plus, minus, plus. We alternate, and so we're going to do entry times minor. So the cofactor expansion is plus A times the minor, and we delete the row and column of A, E, F, G, H. No, E, F, H, I. Okay, and then minus the entry, so minus B times the minor, and the minor, we delete the row and column of B, D, F, G, I, and lastly, plus the entry plus C times the minor, so plus C times the minor, which is D, E, G, H. D, E, G, H. Okay, and so we were hoping that what comes out of here looks like here. So let's do this expansion. So we know that these 2 by 2 determinants, that definition is solid, so we can do E times I minus H times F, minus B times D times I minus G times F, and plus C times D times H minus G times E. Okay, if we expand, so we're getting AEI minus AHF minus BDI minus minus plus BGF, and then plus CDH minus CGE. Now let's just take a look at what we have. Our positive terms AEI, BGF, CDH, AEI, BFG, same thing, CDH, so that's looking good. So let's write those at the beginning. So we've got AEI plus BGF plus CDH. And then our negative terms, or we're going to factor out that negative sign, so minus, and we've got AHF, which is here, confused myself for a second there, minus BDI, that is IDB, and CGE is exactly there, so we get minus AHF, not B, AHF minus, so now we factor out the minus, so plus BDI plus CGE, and indeed we have the same expression, the same as Sarris's rule. So that means that these definitions that we gave before match the cofactor expansion, and so actually if we want to do a 2 by 2 or a 3 by 3 determinant in the future, we have a choice. I mean, the 2 by 2, I don't understand why anybody would ever want to do the cofactor expansion. It's so much quicker just to write the AD minus BC, but there's an argument to be made that this cofactor expansion isn't really all that much longer than Sarris's rule, and so moving forward, when the determinant of a 3 by 3 occurs, we have a choice of methods. Either the definition that we gave as Sarris's rule, or this new method, cofactor expansion. We did row 1 here, but it can be any row or column. It doesn't have to be row 1. If we'd done column 1 or column 2, row 3, doesn't matter, we would have gotten the same value. So in the next videos, we're going to do some examples using this new cofactor expansion, this new definition of the determinant.